Okay, welcome to calculus. This lesson is area between two curves. We want to start with a quick review. Recall that area under a curve is calculated using the definite integral and that it represents the area between a curve and the x-axis. You'll see here in the first example that I have a region above the x-axis, and that's going to give us a positive result or a definite integral greater than 0. And here in the second example, we have a region below the x-axis, and that's going to give us a negative result, an answer less than 0. Just to practice some of these concepts, we see that we have a curve that goes below and above the x-axis, and we've been given some data points here. The region A has an area of 2.87, but because that region is beneath the x-axis, that definite integral would be a negative 2.87 from negative pi to 0. Region B has an area of 1.43. Since that region is above the x-axis, the definite integral would be positive for that region. And region C has an area of 0.71. And again, because it is below the x-axis, the definite integral for this region would be negative. So we can answer question 1, which asks for the definite integral from negative pi to pi. So negative pi to pi means that we have region A and region B. Now, area is always given to us in terms of positive values, but the definite integral can give us areas that are positive or negative, and that just means direction. Negative is below, positive is above. So for question number 1, we would need to take region A and region B, which would give us negative 2.87 in terms of a definite integral, and positive 1.43. And when we add these together, we would get negative 1.44. For question 2, we would be looking at this function from 0 to 2 pi. So that means we would be taking region B and region C. In terms of a definite integral, region B is positive 1.43, and region C is negative 0.71. This would give us a final answer of 0.72 for this definite integral. For question 3, we're going from negative pi to positive 2 pi. That is the full length of this curve we have here. So we would have region A plus region B plus region C. This would be negative 2.87 plus 1.43 minus 0.71, and that would give us a final answer of negative 2.15. And in question 4, you see that there are absolute value brackets here. So that would be the absolute value of A plus the absolute value of B plus the absolute value of C. We would treat all of these as positives then. And we would get a final answer of 5.01. So this is just some concepts with definite integrals, understanding we can get results that are negative, results that are positive. And we're going to use some of this to help explain how area between two curves works. So area of a region between two curves, if f and g are continuous functions on the closed interval ab, and g of x is less than f of x, for all x in the interval, then the area of the region bound by the graphs of f and g and the vertical lines x equals a and x equals b is given by this formula. So area is the definite integral from a to b of f of x minus g of x in parentheses dx. And something that we want to use when we're doing this is a Riemann rectangle. When we first did definite integrals, we derived them from the Riemann rectangles, and we're using them here to say this is the top of the rectangle, this is the bottom of the rectangle. And to find the height of our rectangle, we do top minus bottom. That gives us the height. And the width, of course, is delta x. That's part of our integral. And you'll see that I'll draw Riemann rectangles through the presentation to keep referring to it. And it's only used as a guide to help us make our decisions. So top function minus bottom function gives us the height of the rectangles that we want for our definite integral. And that's what we have here. The area between two curves formula can be expressed as the integral of the top curve minus the bottom curve. Results are always positive. That's something you want to keep in mind when you're solving definite integrals, which represent the area between two curves. If you get a negative answer, then you have made a mistake. The definite integral for the area between two curves is always positive, and we have three cases we can consider. Case 1, two curves above the x-axis. Case 2, where we have two curves below. And case 3, where one curve is above and one is below. So let's just look at those. So here's case 1. So here's our top curve and our bottom curve. And if we look at our top curve here, we see that this has the bigger positive area. And we look at our bottom curve, it is the smaller positive area. So a large positive number, subtract a small positive number, gives us a positive result. This one should be straightforward, but we want to look at the other cases to show that, yes, the area between two curves will always be a positive result. So once again, here's our top and bottom curves. If we were to draw our Riemann rectangle between here, it's always top minus bottom to find the height of the rectangle. And if we look at this first definite integral, the definite integral from 1 to 5 of f of x dx is going to equal a negative number. It's going to be less than 0, right? It's beneath the x-axis, as we saw in our review at the beginning of this presentation. And we see that the same is true here for g of x. From 1 to 5 for g of x dx, we're going to get another negative number. But we see that the first one is a small negative, and the second one is a large negative. And we're subtracting. So when you subtract a negative, that double negative makes this an addition problem. So I'm just going to throw some numbers. Imagine this was -2 minus -4. The result is going to be positive. So when we have the area between two curves and both are below the x-axis, the top curve will give us a smaller definite integral that is negative, and the bottom curve will give us a larger negative value from the definite integral. And when we subtract that larger negative, it becomes addition and turns everything into a positive. And this last case, case 3, we see that we have a curve above the x-axis. So again, if we draw our Riemann rectangle in here, the top curve minus the bottom curve, well, the top curve is going to give us a positive result. And then we're going to minus a negative result. And when we minus a negative, that becomes a positive, so we get a positive. So that's just a quick run through of why results are always positive for the definite integral. We looked at the 3 different scenarios that can come about from the area between two curves, and we saw that all 3 of them give us positive results. So now we're ready to do our first example. We see here that we have a function f of x on top and g of x on the bottom here. F of x is the parabola, G of x is the line. That's how I identified them. If you have two curves and you can't identify them, then you plug in some x values to see which one has the larger output value for the same x. So if I plugged in f of 2 and g of 2, if I didn't have a graph handy, I can find out which curve is the top curve, because f of 2 would give me a larger y value than g of 2 would. So then I would be able to say this is top and this is bottom. So we can identify top and bottom without being given the graphs. So now that we've looked at how to identify top and bottom, we want to write our definite integral. Area is the definite integral. We see our shaded region starts at 1 and it ends at 4. We want to take our top function and minus our bottom function and put these all in brackets. And now we can simplify the algebra here. We can say that area is equal to the definite integral from 1 to 4. And if we combine like terms and distribute our negative, we're left with 1/8 x squared plus x. And now we can integrate. All right, so we just use the power rule for polynomials. You add 1 to the exponent, divide by the new exponent. So we have 1/24x cubed plus 1/2 x squared. And now we have to apply the fundamental theorem of calculus, which says evaluate the bounds by taking f of b minus f of a. So area is equal to 1/24, 4 cubed plus 1/2, 4 squared. That's the f of b. Let's minus the f of a. Since we're plugging 1 in, we can see that we're going to get 1/24 plus 1/2. And again, this is our f of b minus f of a using the fundamental theorem of calculus. And now we can evaluate this, and we'll get 243/24, which is 10 1/8. Or if you prefer as a decimal, 10.125. So that was a straightforward example. We had a parabola and a line. Both curves were above the x-axis, and we got a positive result as expected. This is a classic trig example. Every calculus book does an example like this at the beginning of area between two curves. And we just have to have some caution here because there's a lot of sign changes that happen, positives, double negatives that we have to account for. And as long as we're careful and take our time with it, we should not overlook the signs or have a computation error. So we see the shaded region here. And we should be able to identify that cosine starts at 1 and sine starts at 0. So this region has sine as the top curve and cosine as the bottom. When are sine and cosine equal to each other? Well, you can look at a unit circle and you see that they're equal at pi over 4. They're both positive √2/2. And if we go all the way around at 5 pi over 4. So we should be able to write this definite integral. And that represents the area between these two curves for the first bounded region. For the first bounded region between sine and cosine for x greater than 0. So now we just have to integrate. The antiderivative of sine is negative cosine. The antiderivative of negative cosine is negative sine. And we put our bounds up here. I use lots of brackets to keep my f of b and my f of a organized. And if we look up cosine of 5 pi over 4, it's negative root 2 over 2. Don't forget the negative in front of the cosine, so we see a double negative is occurring here. We're subtracting sine of 5 pi over 4, so that's another negative root 2 over 2. And then there's a negative in front of cosine. Cosine of pi over 4 is positive root 2 over 2. We have another negative in front of sine. Sine of pi over 4 is positive root 2 over 2. And we see in this first bracket for f of b, the double negative makes this positive root 2 over 2 plus root 2 over 2. So we have 2 root 2 over 2. And then there's a minus. And in here we have negative 2 root 2 over 2. But that double negative becomes a positive. So we have 4 root 2 over 2, which simplifies to 2 root 2. So again, I'm going to emphasize, keep your brackets, write out your f of b minus f of a, make sure everything's organized, your subtractions and double negatives are carefully accounted for, and then you'll get to the correct answer. It's very easy to make an oversight, work through it yourself, see that you get the same answer. Okay, so here's example 3. This is a two-integral case. The reason that we have a two-integral case here is because this region has a different top and bottom function from this region. Here we see that the cubic polynomial is on top and the line is on the bottom, where here we see the line is on top and the cubic polynomial is on the bottom. So I'd like to just call this region 1 and region 2. My area is going to be region 1 plus region 2, so I'm doing two separate definite integrals. So for region 1, it looks like it's going from negative 1 to 0, but you should always verify that by setting the two equations equal and solving. And when you do, you'll find that you do get negative 1 and 0, but don't always trust the graph. Often the graph is off by a small amount just to make sure that the student is verifying the bounds and not just going off of the graph. So in region 1, we see that the cubic polynomial is the top curve. So it's top minus bottom. We'll put 2x cubed minus x squared minus 2x. Now we want to subtract the bottom curve. That's just x. Put that all in brackets and our dx. So we'll solve region 1 first. We can combine these polynomials together. So we get 2x cubed minus x squared minus 3x dx. And now we can find the antiderivative. Add 1 to the exponent. We're using the power rule, so this becomes x to the fourth. When you divide by 4, 2 over 4 is 1/2. So we have 1/2 x to the fourth minus 1/3 x to the third minus 3/2 x squared from negative 1 to 0. Now we're using fundamental theorem of calculus. Since all of these terms have x's, when I plug 0 in, we're going to get a 0 minus 0 minus 0. So that's the f of b. That one's simple. And now the f of a from the fundamental theorem is 1/2, -1 to the 4th, minus 1/3, -1 to the 3rd, minus 3/2, -1 squared. So region 1 is 0 minus -1 to the 4th is 1, so that's 1/2. -1 to the 3rd is -1. -1 times -1/3 is plus 1/3. And -1 squared is 1, so we have minus 3/2. So for region 1, we'll get these all to be as common denominator. So this is going to be 3/6 plus 2/6 minus 9/6. Don't forget I have a minus in front of this bracket. So that gives us 5/6 minus 9/6 is -4/6, but the negative out front makes region 1 equal to positive 4/6 or 2/3. Now we want to do this again for region 2. Region 2 we see is going to go from 0 to 3/2. Again, I got that answer by setting these two equal and solving for the intersection points. So we're going to work this out on another slide. So we're going from 0 to 3/2. And this time it is the linear function that is the top curve. So it's going to be x minus, and then 2x cubed minus x squared minus 2x. And dx. So let's simplify our polynomial. We get negative 2x cubed minus, make that a plus, x squared plus 3x. We've combined all the like terms, and you'll find that the antiderivative is the same, just with different signs. And we have different bounds to plug in. So this is our f of b minus f of a, but we see f of a is 0 again. So 3/2 to the 4th power. That gives us 81 over 16, but there's another 2 here. So it's 81 over 32 with a negative. Plus 9/8. Plus 27/8 minus 0. So now we want to just combine all the like terms. And when we do that, we're going to get 189 over 96. And if we take region 1, which was 2/3, and region 2, which is 189 over 96. We can find the total area, and I'm going to convert this to a decimal just to make it more manageable. And we get an area of 2.64. Okay, so let's go back to the initial problem. When we first saw this problem, we identified that we needed two integrals. We needed two integrals because my Riemann rectangles here have a different top and bottom function. We saw that a change occurred in the top and bottom functions defining the rectangles. Whenever that happens, we need to split up the integral and say, where does that change occur? And we saw that at this point, at 0, is when the top function changed from region 1 to region 2. And that is why we needed to have a two integral case. So now, a question that might come up is, could there be a three integral case, a four integral case? Sure, that's all possible. We'll limit our multiple integral cases to 2, no more than 3 as a maximum, but mostly to 2. And you'll have to write separate integrals where you switch the top and bottom functions and have the correct bounds of integration. So we're going to end that here. I have another example, which is a two integral case, but it's a long example. I'll save that for a separate video. So watch the video, take notes, send me questions, and then complete your assignment.